So hello, welcome back everyone. So I think we're going to start. So welcome to the Coffeeshop Astrophysics. Today we're going to present the last talk of the semester. So we will be back in September. So stay tuned to our social media to know exactly when are we coming back. So as always, if you have an idea of or a future talk or a topic you are interested in, then you can fill a form in our website, and then we can hopefully talk in a future talk about it. And if you happen to be in the Madison area on May 21st, there will be Astronomy on Tap. So this is a similar thing organized by grad students at University of Wisconsin-Madison. So if you go there, then we recommend you to see the talk, and because there will be also science talks and astronomy talks. So who are we? So we are a group of physics grad students and postdocs at the Leonard E. Parker Center for Gravitational Cosmology and Astrophysics at the University of Wisconsin-Milwaukee. And today your speakers are myself and Sarah. So you might hear the news that recently Coffeeshop Astrophysics was the 10th anniversary. So then today we're going to take you through a journey through the six groundbreaking discoveries of the last 10 years of astrophysics. So these discoveries weren't known when this coffee shop started. We're going to talk about gravitational waves, fast radio bursts, the black hole image, the neutrinos, exoplanets, and the oldest galaxies as seen by the James Webb Telescope. So I'm going to start talking about gravitational waves. So in February 2016, there was this news all over the planet when it was announced that there was the first direct detection of gravitational waves. So what LIGO, so the Laser Interferometer Gravitational Wave Observatory, what they saw is that there's ripples of the space-time when the black holes merge. So as 400 years ago, Galileo pointed the telescope and opened a new window of the modern observational astronomy. This detection opened a new whole world, a new window in which we can observe our universe. So this is one of the most important observations of this century. And as some of you might recognize, there's a familiar face in there, which is Einstein. So it was actually a prediction of Einstein's theory of general relativity. So what Einstein imagined, so he thought about our universe as the sheet, and gravity as the deformation of that sheet. So we can think like if we have a mass, then this mass will curve the space-time. And then the stronger the gravity, then the stronger is the deformation. So when this mass moves through this space-time sheet, then what we will observe is these ripples in the space-time, which are the gravitational waves. So gravitational waves are invisible waves that travel at a velocity of 186 miles per second, which is actually the velocity of light as predicted of the theory of Albert Einstein. So what we will see is that these waves stretches and squeezes anything that it goes in through their paths. So what we are looking here is just a vastly exaggerated effect what gravitational waves do on Earth. So this is actually not as hard as this one. These gravitational waves are actually very subtle, so we won't feel anything like that. But so gravitational waves are really hard to detect. So what LIGO did is that they actually use laser interferometers. So for us to be able to observe gravitational waves, what we do, or scientists do, is that there's a laser that the beam is split, and they send these lights through this tubes, which are large perpendicular tubes, and the two beams bounces off mirrors, and then these tubes have exactly the same measure, the same length. So if the light travels and there is no gravitational waves, or there is not any external effect, what we will see is that the light waves will cancel each other out, and then in our detectors we will not see any light. However, if a gravitational wave passes through, what it will do is that it will modify the length of those mirrors. It will distort the space. So then what it will cause is that these light waves will recombine in a wave that these will no longer cancel each other, and then we will see some light at our detectors. And then what we are going to be looking is that how those distances of these mirrors changes, and then we will be able to measure the gravitational waves. So this is what actually it was measured by LIGO. So this is the data that they got. So LIGO consists of two observatories, one in Hanford, Washington, and the other one in Livingston, Pennsylvania. So the orange one is from Hanford, and the blue one is from Livingston data. So what you can see with a little bit more light color is the line that as predicted as Albert Einstein theory of gravity. So of general relativity. So in the x-axis we have the time, and in the y-axis we have the strain. And the strain is just the fraction of the difference of the measure of the distances that they measure with the detectors. So what we are looking here is how these tubes change in distance, and then that's how we were able to see the gravitational waves. And in the bottom panel of this plot, you can see the both data combined from both observatories, and then you can see that they both are in agreement. So we can see that they detected the same thing. So then we can confirm that it was a gravitational wave detection. So a few years later, there was also again gravitational waves all over the news, but these times the gravitational wave background was evidence for the gravitational background was found. And how do we measure these things? So actually, it was last summer when this news came out, and then what we do is that scientists we use pulsar timing arrays to being able to observe these ripples of space-time that are produced all over the universe and by massive objects. So then I will just briefly introduce how pulsar timing arrays work. So we actually use pulsars, which are extremely dense rotating neutron stars that are formed in explosions of massive stars, and they have very strong magnetic fields of the order of 1 billion times stronger than the Earth's. So every time a pulsar rotates, it emits a beam of radiation, and we will able to detect these beams. So pulsars can rotate very, very fast. They can rotate up to 43,000 rotations per minute, or the order of 1.3 times per minute. So that's the fastest and the slower pulsar that we know. So in order to observe pulsars, what we do is, because these are very tiny objects, they have only a radius of only 10 kilometers, and they are very far away, then what we need to do is to observe them through other ways of light. So here we have a plot of the electromagnetic wave spectrum, which it gives us an image of all the different ways of light. And in these we have it goes from longer wavelengths, which is radio waves. So a wavelength, we can think about it as the distance between two of these peaks. So the longer the wavelength, we have radio waves. For shorter wavelengths, we have gamma rays. So in order to study pulsars, what we do is we actually observe radio waves. And for observing radio waves, what we do is we use radio telescopes. So radio telescopes are big dishes, so the radio signal travels through the space and comes to the dishes. So the dishes then send this signal to the antennas, and then the currents antennas that are amplified, digitized, and recorded through the computers. Okay, so we use, well, for the gravitational wave detection, what we actually did is to use several, most of the biggest or largest radio telescopes in our planet in able to detect this gravitational wave background. And in our case, and in the US, we actually use the North American Nanohertz Observatory for Gravitational Waves, in which we use these 4 telescopes that are listed here. And so we can say proudly that the members of Coffeeshop Astrophysics, including myself, are part of this collaboration. And we worked in the discovery of the evidence to find the evidence of the gravitational waves. So we use these telescopes to measure the time of arrival of each pulse of the pulsars. So what we do is that we every time we observe a pulse, we measure it, and then this we gain more information, and after this we will get a model. In this model, we will use it to try to predict when the next pulse will come. And so once we do the comparison between the model and the observed data, we use this pulsar timing technique, which is what we want to achieve is to unambiguously account for every rotation of the pulsar over the years. So we use pulsar timing from different pulsars from all over our galaxy in order to find the correlated the perturbations in the signals of those pulsars. So we use the pulsars in our galaxy as our gravitational wave detector. So these gravitational waves will perturb the signal of those pulsars, and we will be able to measure it. We are able to measure it. So to talk about the present and the future of gravitational waves, we need to talk about the gravitational wave spectrum. So I've told you about it, that we are able to detect the gravitational waves of merging objects by using ground-based interferometers like LIGO. And we also are able to detect gravitational waves emitted by supermassive black hole binaries by using pulsar timing arrays. But you might see that there is some gap here, and for able to observe these frequencies of gravitational waves, we might need to, in order to observe the galactic white dwarf binaries waves, we might need to build space-based interferometers. So just recently, the LISA project was approved, and then hopefully in the next 10 years, it will start the building of these kind of space-based interferometers, and in a few decades, we might be able to be sensible or to detect gravitational waves in this frequency range. And then there is also really gravitational waves, but we are not going to talk about it today. But if you are interested, then there is a full talk dedicated on gravitational waves from Coffeeshop Astrophysics. So if you're interested, then you can go to this our YouTube channel and look at this talk. Okay, now I'm going to talk about fast radio bursts. So fast radio bursts, or FRBs for shorter, are bursts of radio waves lasting a few thousandths of a second. So these are a burst of radio waves that are happening somewhere in our universe, and that we don't know what is causing them. So the first was found by Lorimer and collaborations in 2007 by using the Parkes Radio Telescope in Australia. So now we know that if we could observe our entire sky during the whole day, what we will be able to measure is that there are of the order of thousands of these bursts of radio waves in a day. So this is just a map. If we can imagine the whole sky in a 2D dimension, we might be able to see something like this. So we know we can detect something, but we don't know what is causing this signal. So now I'm going to show you a short video of how these bursts are produced. So there's a sudden burst somewhere in our universe, maybe in another galaxy. And as this signal travels through the space or through the medium between the source and our Earth, then this signal will interact with the medium. So we know that the medium is filled with free electron particles. So the more energetic the signal, the higher the frequency of the signal, it will travel faster. So it will reach the Earth. Now it's coming, it's getting there. So it will reach the Earth, and it will we will be able to detect this signal with our radio telescopes. So this signal is then transferred to our computers, and then what we might be able to see in our computers is something like this. So this is a characteristic signal of a fast radio burst. And we know that this signal is coming from outside our planet, since we know there's a delay. And this is what we will see in our data from our telescopes. So here we have on the x-axis the time, and the y-axis we have the frequency. So we can see that higher the frequency, the signal will arrive earlier, and the lower the frequency, the signal will come later. So if we correct then for this dispersive delay, then we might be able to see is this peak, very nice peak. So this is the signal of the fast radio burst. So we are detecting these FRBs. So, but however, we still don't know what is causing these things. There are a few models, a few theories, but we know that it's a very high very energetic burst, and that it only lasts for a few milliseconds. So it should be very something very compact and very powerful that produces this signal. So in order to find out what these bursts are, what we actually need to do is try to find them more, so then we can get more information. So in November 2012, there was the discovery another burst. You can see here, you might see there is the characteristic signal of a fast radio burst. And then if we correct for the delay, then we can get this very nice peak. But the characteristic thing about this FRB was that it was later found in other dates. So that means that the FRBs might repeat, so can repeat. So we didn't know about it before. So after the signal is repeated, then we might want to see where the signal is coming from, because we know it might repeat, so then we can observe it again, and we can get data from all other telescopes, and then we can make a map in the sky, and then we can get an idea where it is coming from. So in that way, there was use of other telescopes. And then this is using an interferometer, so several radio dishes combined the signal, and then they get an idea of the where this signal is coming from in the sky. And then after that, they were able to observe these sources in an optical telescope. And this is the image here, and you might see there is something here. So they found where this signal was coming from. And they found actually that it was a dwarf galaxy. So these signals might produce in other dwarf galaxies. The leading model that produces these signals are magnetars. So magnetars is just another type of neutron stars that are ultra highly magnetized. So the magnetic fields of magnetars are even stronger than pulsars. So these magnetic fields are also unstable, and that can cause massive explosions that can be seen in X-rays and gamma rays. However, not radio bursts were known from magnetars, and there is also only 30 of these objects known to this date. So then if we are getting thousands of fast radio bursts or FRBs, how 30 magnetars can be producing all these signals? So this is something that it was a question until in 2020 there was the detection of this double burst. So you can see there was it was the same FRB, but with two bursts at the same time. And then at the same time, there was a detection of an X-rays. So here we see the peak in X-rays. So there was, and we know that magnetars have this kind of behavior. So then we can say that there was an FRB and magnetar association. So there actually magnetars might be able to produce these kind of FRBs. Here we have, so far we know that these are astronomical, astrophysical sources. They can repeat, we are not sure if all they repeat, and if we know that there can be extragalactic, but there can be also produced in our galaxy, and these FRBs can be produced by magnetars, but we are not sure if magnetars are the only source that can produce these FRBs. So hopefully in the next 10 years, we might get more idea of what an FRB is. So now I'm going to move to the black hole image. So again, astronomy was all over the news in April 2009, and it was because astronomers were able to image for the first time ever a black hole. So yes, black holes were also a prediction of Einstein's general relativity. So this theory just tells us how tells the space-time how the matter how to move, and the matter tells space-time how to curve. But what a black hole is? So a black hole is a region of space with such an immense gravity that nothing, not even light, can escape it. So if we want to take an image of a black hole, then how can we do it? But okay, so just here I have a sketch of how of the structure of a black hole. So black holes are what we actually they have a singularity. So in the singularity is that they have infinite density in just a single very tiny point. So then there's the event horizon, which is the radius of this singularity, and this is like the end point. So once the light or matter passes through this to this radius, then nothing can escape from the black hole. And then there's also relativistic jets. So matter or stars, matter from stars or dust can come into the black hole, and these will produce these relativistic jets of radiation. And then the gas and dust and matter will that the black hole is accreting will be producing an accretion disk of heat. Will be heating matter. So we will be able to detect this matter in X-rays and other wavelengths. So that's what we might be able to see black holes. So then as what I was saying, how can we look at black hole? So we can say the black hole is there, right? Because we cannot see. But so in order to see a black hole, maybe a good idea could be put some light behind it, so then we can see there is something there. But however, what astronomers did was to use different radio telescopes from the planet, and then use a technique which is called interferometry, which is just summing the signals from all these telescopes. And this allows us the astronomers to reach a very high angular resolution. So an angular resolution tells us how, if we point our telescopes in a point in the sky, we might be able to, if there are two sources, we might be able to resolve those two sources and not only one. So in order to take an image of a black hole, we need that the telescopes reach the angular resolutions of about 35 microseconds. So this is arc seconds, sorry. So this is equivalent to standing in New York and then being able to read the date in a quarter in Los Angeles. So this is very impressive thing. So astronomers then ask the black hole to stay ready for the picture, right? So that's how they were able to obtain the first picture of a black hole, and it was actually the black hole that is in the center of a galaxy, which is known M87, which is 50 million lights away. But however, this black hole is one of the most massive black holes that we know. So this was because that's why the astronomers were able to take the image of this black hole. So a few years later, more recently, there were also the image that of the black hole that is in the center of our own very own galaxy. So this is 26,000 lights away. However, this black hole is a little bit, it's a lot smaller than the other one. So that's why it was a little bit harder to take the image of this. So, but if you want to know more about it, there's also another full talk of Coffeeshop Astrophysics in which you can learn more about images and how we can see black holes. So that's it for me. I will hand it over to my colleague.
Hi. Okay. So we'll continue our journey of things that we actually discovered in astrophysics in the last 10 years. And now I'm going to talk a little bit about neutrino astronomy. But before we really talk about the discoveries on neutrino astronomy, we need to know what neutrinos are. And neutrinos are particles. And they are very strange particles. So the first thing is that they have no charge and very little mass. Actually, for a while, scientists think that neutrinos actually had no mass. Now we know we haven't measured it, but we know it's very, very little. They are very abundant in the universe. So we know that every second, 100 trillion neutrinos passes through our bodies. This is 1 followed by 14 zeros. It's a lot. And we don't feel them. This is because they are very hard to detect. They don't like to interact with matter. They don't like to interact with anything. And for this reason, they got the name ghost particles, because they are just like little ghosts. And before 2014, we only had 2 confirmed sources of astrophysical neutrinos, so neutrinos that comes from space. The first one being the sun. We know that neutrinos are formed beside the stars when we have the nuclear reactions, and the sun is very close, very nearby. We can detect neutrinos from the sun. And the second one was a supernova that happened in 1987, supernova 1987A. This picture here specifically is from JWST, so it's very new. And the supernova happened relatively nearby the Earth on the Grand Magellan Cloud, so it's a dwarf galaxy very close to us. And one interesting thing about the neutrino detections that happened in this supernova is that we actually detected the neutrinos before detecting light. And then you may ask, how on earth this happened? Because neutrinos travel almost the speed of light, but we know that light travels at the speed of light. How neutrinos got here first? And the reason for that is because neutrinos don't interact with anything. This makes them hard to detect, but also this means that when the supernova happened, neutrinos started to travel through the Earth right away. But light actually interacts with the matter from the supernova for a few hours before traveling to us. So every time happens a supernova nearby, we actually are going to find it from neutrinos before finding from telescopes. So we can prepare ourselves if we have a neutrino warning, and then point our telescopes to supernova, because they will tell us first. And the best neutrino detector we have on Earth right now is IceCube. And you may find it by the name. We also have a picture here where IceCube is, but it's Antarctica. But even being in Antarctica, IceCube has a heart in Wisconsin. And you may ask why. This is because IceCube was developed and supervised by UW Madison. So it is a proud Wisconsinite. And how IceCube detect neutrinos? Because I've just said they're very, very hard to detect. So I have a video for this. So what happens is that we have a neutrino that came from space, and this neutrino will interact with the ice, the atoms in the ice. And this will cause some radiation. And what the detector actually captures is the radiation that comes from this interaction between the neutrino and the ice. So we have a lot of those detectors, and when the neutrino interacts, they receive a signal that a neutrino is passing through IceCube. As I said, neutrinos doesn't really like to interact with anything, so Our scope only see one neutrino forever, every 500 trillions that passes through the observatory. Again, if you want to ask how big is this number, is a 5 followed by 20 4 zeros. So it's a lot. 26 zeros, I'm sorry. So still, IceCube haven't detected that much observations in the last 10 years. But it's much more than what we had before, because you can remember I said that we only had 2 neutrino sources from before. And one of them was the sun. So after 2014, we actually had 3.5, because one of them is a candidate, so I'm counting as a half event. We are not sure if it happened, events from neutrino detections. So we have one from a blazar, another one from the tidal disruption event, another one from the active galaxy nuclei, and then one that came from our own solar or own galactic plane. One interesting thing we can see here is that I'm not going to explain what all those events are, all those astrophysical objects, but all of them have supermassive black holes. So I promise you that we are going to do a talk about neutrinos in the near future, maybe next semester, maybe next year. But what we can know right now is that those high-energy neutrinos that we detected all come from supermassive black holes. And supermassive black holes like to produce those particles. But still, we come from 2 sources to 6 or 5. It's a lot more, but we have a lot to discover still about neutrinos. 6 events, 5 events, it's still very, very little. So neutrino astronomy is in its baby steps, but we did see a lot of improvement in the last 10 years. And we will continue to see, because IceCube will be upgraded in the next 10 years, and it will become a little bigger. So we'll certainly have more discovery come from neutrinos and IceCube. And we didn't have a talk about neutrinos, but we had a talk explaining exotic telescopes before. IceCube is certainly an exotic telescope. So if you want to know more about IceCube and how it works, we have a talk about it. Next thing that we really had a lot of new information was exoplanets. So I have a video here that we started counting on exoplanets in 2012. And we see that in the beginning of 2014, so 10 years ago, we had less than 1,000 exoplanets confirmed. And the number just started to grow. And we reached the mark of 5,000 exoplanets in 2022. 5,005. As of right now, we know 5,616 exoplanets. And 40% of them are what we call gas giants, so they just look like Jupiter. Maybe they can be even a little bigger. 35% of them are what we call Neptune-like. They are the size of Neptune. Then we have 31% that we call super-Earths. And super-Earths actually can be like Neptune, but a little smaller, or like Earth, but a little bigger. So we can measure the size, but until we do extra studies, we cannot really know what forms them. And only 4% are on the size of Earth or smaller. And most of those exoplanets were discovered by a telescope called Kepler from NASA. Kepler mission worked for almost 10 years, from 2009 to 2018. And it discovered 2,662 planets. So, as I said, almost half of them. And Kepler uses a very specific way of measuring exoplanets. So we have different techniques. I'm not going to talk about all of them here. We wouldn't have the time. We need a specific talk from exoplanets to talk and cover all the methods. But I'm going to cover the method of Kepler, because it's the one that we have the most discoveries. So the method is called transit. And what happens is that when the planet passes in front of the star, it eclipses a little bit of its brightness. And this is little tiny bit of brightness that is eclipsed is what we measure. Of course, we need to measure it for some time, because it can be just something random passing in front of the star. So to be sure it's a planet, we need to see this brightness dropping periodically. But if we have this measurement, then we found the planet. And you can imagine that this drop in brightness is actually very, very little. And it is. I have here a picture that is actually from JWST, but that shows this very well. So when the planet's behind the star, we have 100% of brightness from the star. But when the star light is blocked by the planet, we have this drop. But this drop is only 0.1%. So 99.9% of the light of the star still reaches us, but because of the 0.1, we can detect an exoplanet. But detecting exoplanets is fine, but finding some of them that is habitable is even nicer. So how can we do that? The first thing we do is try to find where the exoplanet is compared to the star, because we usually use what we understand from life on Earth. So life on Earth needs water. And what we want is planets that can have liquid water, not vapor, not ice, but liquid. And in order to measure this, we just calculate how much starlight the planet gets, because if it's too much starlight, then we'll get vapor. But if it's too little starlight, then the planet will have ice. And what we want are exoplanets that are what we call habitable zone. But this is not enough, right? Because we can have a planet in the habitable zone, but still its composition is not good enough. In the end, I'm going back to the slide. Look what we have in the habitable zone. We have Mars. Mars is so nearby, but we haven't even found life on Mars yet. So we'd like to find an exoplanet that we can be sure has life. So for that, we need to observe the atmosphere of the planet. But you can imagine how hard it is to observe the atmosphere of a planet. So before I explain how can we observe the atmosphere of a planet, I want to show the spectrum of a star. So if you really like astronomy, certainly you saw this curve before, but we have to show it for completeness. So what we have here, like this continuum image, is just like the star emitting, because if it's a hot, glowing fireball. So forget about the indentations for now, just think like this curve, just the shape of it. And this is what we call black body emission. But then we have the indentations. So we have this drop here, and then we have this drop. We also have those drops here. And what those drops are is what we call absorption lines. And in this star specifically, we know that those absorption lines here tell us that the star has hydrogen. So what we want is the spectrum of a planet. And then we can try to find what elements are causing those changes, those bumps in the planets. But how can we observe the planet? Because in the end, the planet's with the star. So I think it's a very ingenious technique, but what people do is, first they observe what we call combined spectrum. They take a snapshot of the spectrum when we have the planet and the star together. The planet is certainly showing up. And then we wait for the planet to be behind the star and get another spectrum. We do one minus the other, and what is left is the planet spectrum. But you can imagine how hard it is to do that, because the spectrum of the planet is so less bright compared to the spectrum of the star. Wouldn't it be so amazing if we had this like groundbreaking new telescope that is the best of its generation? And of course we have. And if you're talking about the discovery of the last 10 years, everyone was waiting. JWST had to show up in the presentation, and finally it's here. And I'm going to talk about one of the discoveries of JWST that happened last year. So we had this atmosphere of an exoplanet known as K218b. There are a lot of nice things there, things that we have on Earth. First one being, we have methane in the atmosphere. Methane is good. We like methane in the atmosphere. We have carbon dioxide. Also nice, we have a carbon dioxide on life, on Earth. But what really made the news, if you ever saw this, was the presence of this molecule here, dimethyl sulfide. And then you may ask, why finding this molecule is so important? The first thing I'm going to say, this discovery of this molecule is not confirmed yet, so we need more observations. But if it was confirmed by JWST, dimethyl sulfide on Earth is produced by planktons on the ocean. So this would be the first biomaker that we would find on space somewhere else not on Earth. So this would be very exciting. As I said, don't get too excited on that, but maybe we'll find this really on the news chain. It's confirmed in the next 10 years. Would be so nice. New JWST observations are scheduled for this object, so stay tuned for that. Of course, we expect new JWST discoveries on exoplanets in the next 10 years, but I want to talk about what we can expect outside of JWST. And I'm going to keep special attention to two telescopes, Plato and Ariel. Plato is expected to launch in 2025, so next year, and Ariel in 2029. Both of them are from the European Space Agency. And why I'm going to keep special attention to them is because both of them, their main mission is to observe exoplanets. So Plato will have a mission very similar to Kepler. Their main mission is to identify new exoplanets. So we now have more than 5,000. But with Plato working, we can expect to have even more in the next 10 years. And Ariel, its main mission is to observe the atmosphere of exoplanets. So what Ariel wants to do is get that picture I've just showed in the previous slide and just observe it for more than 1,000 exoplanets. And then you may ask, why put in a telescope in the sky to observe the atmosphere of exoplanets? We have JWST for that, you know? JWST is actually much better than Ariel. So why? But JWST has limited time. JWST has to observe exoplanets, galaxies, stars. So what Ariel will do is just really increase the amount of exoplanets we have observation about the atmosphere. And then certainly the best ones, the most promising, is the ones that we have hints of biomakers, we will reobserve with JWST. So JWST is only used for special cases. And then just like observing a lot of things, we use the least better telescopes. And we have had a few talks about exoplanets before, so how to find all of them, how to find life on the universe and in other galaxies. And we also had a talk on JWST, so if you're interested, please go check them. And the final thing I want to talk about is oldest galaxies. And it's very nice that oldest galaxies is like in the last part of the talk, because this was the one that I think we still have a lot of work to do. There were a few advancements, but there's still a lot of work, and we'll have a lot of think about this in the next 10 years. So the first thing I want to say is that what question we want to answer about this. And what we really want to know is how the first galaxies and the first stars were formed. So the first stars were formed, as far as we understand in theory, 100 million years after the Big Bang. So we have here the first stars. And then we have the first galaxies formed. And we don't really know how this happened, and this is what we really want to understand and observe. And this is one of the main missions of JWST. So just to remind how much better JWST is, I have a deep field comparison of JWST and Hubble. If you like astronomy, you've saw this picture before, but if not, I will explain. So the deep field image of Hubble was taken a little more than 20 years ago. And what they did was pointing Hubble to this very dark part in the sky, a part that there was no stars, very little galaxy. It just seems dark. And let Hubble observe it for a long time. And when Hubble finished it, what they found was like this plethora of galaxies, very old ones. And this changed astrophysics, because we could see that even in this dark patch of the sky, there was so much information, so much to be discovered and learned. And when JWST started, one of the very first images they took was to repeat this deep field image, but with JWST. And then we can compare both of them. And we see how much better JWST is compared to Hubble. We have so much more details, more galaxies. We have those round shapes here, which is like galaxies being lanced. There's so much information. But it's not only because of that JWST is actually so much more interesting than Hubble. One interesting thing that happens is that when the universe expands, and we know the universe is expanding, light expands with it. So in these very old galaxies, when light is emitted with the short wavelength, like we can see here, light emitted with this very short blue wavelength here. when the universe expands, it gets stretched. So we see much more stretched when we receive it. So Hubble is an optical telescope. It's something that I don't think it's talked too much. We just compare one and the other, but they're actually a little different. Hubble is an optical telescope. James Webb is an infrared telescope. So James Webb is much better to see those stretched wave emissions from those old galaxies. And not only because it's better, but because it's an infrared, James Webb can reach a much deeper limit in terms of observing those first galaxies and the first stars than Hubble. And just for curiosity, how can we know that this wavelength was stretched? Because it could be just like a wavelength that was always a little more stretched. And I've talked about those emission lines, absorption lines before when I talked about the star, right? It's like those lines here will tell us about the composition of the galaxy. And what happened when we stretch the wavelength of the galaxy, like the emission that the galaxy is emitting, we also change the position of those lines that talk about the composition of those galaxies. So the far away the galaxy is, more distance those lines are from where they are supposed to be if the universe was not expanding. And that's how we measure how stretched those wavelengths are. And this is what we call redshift. So what is the oldest galaxy that we ever measured? Before James Webb, so here is a Hubble photo. The record was 11.1 in terms of redshift. And if you're talking about light years, this galaxy was formed 420 million years after the Big Bang. So the Big Bang was here. 420 million years after that, we have this galaxy. And then JWST just came, found a lot of galaxies that were much older than that. And our record right now is this one, 13.2. 300 million years after the Big Bang. So we are getting there. We are getting much more information. We are still studying to understand how those galaxies were formed. We are trying to find as much of them as possible to study them. But we are getting to the point that we can understand what happened in those first galaxies. And I just want to give one bit extra information, like a bonus information that is related to galaxies, but doesn't really talk about those super old galaxies that were formed 300 million after the Big Bang, is that a few years ago, this happened in 2022, we discovered the oldest star that we've ever found. It's not part of the first stars, as I said, that were formed just 100 million years after the Big Bang. This one is 20.9 billion light years away. But if you see here, we have this point. And this point, where my pointer is, so I'm going to take it so you can see, is a star. And we can see the star that far away. And you may ask, how can we do that? And it's because the galaxy where this star is, this what we call here distant galaxy, happens to be exactly behind a galaxy cluster. And then what happens is something that we call gravitational lensing, when actually the light of this galaxy is magnified as if we have a magnifying glass. And then we actually can see this galaxy much brighter than before, and we can really observe a specific tiny star, which I think is pretty amazing. So a lot of science has still been done from JWST on these oldest galaxies, but we also can expect work in other wavelengths. So what we can expect the next 10 years is that we have this very amazing telescope. This is Square Kilometer Array. It's a radio telescope. Its main mission is to observe those oldest galaxies. And this telescope is not just like a giant dish, a giant antenna that will observe the sky, but is actually a composition of hundreds of dishes and hundreds of thousands of antennas. So the dishes are in South Africa, the antennas are in Australia, they cover a really large area, and together they will be the best radio telescope we have. But not only in radio, we also have new incoming things in optical. So the next 10 years, we'll have the new generation of optical telescopes working. Optical telescopes that will actually be much better than Hubble. They will not be space telescopes. What they did was build 30-meter telescopes on Earth. So we have the 30-meter telescope that is supposed to be in Hawaii, but if you look at the news, this construction is in a important site for native Hawaiians, so there's some discussion of whether or not this construction will happen, what is the timeline. So actually this one probably will not be ready in the next 10 years, but the other two will. So we have extremely large telescope, 39 meters on Chile. First light is expected to be in just 4 years. And then we have the Grand Magellan telescopes, also in Chile, so both of them in South Hemisphere. This one is 2029. So this one here is the extremely large telescope. This other here in the bottom is the Grand Magellan telescopes. And so we have an idea how big they are. We have like a baseball court here, we have a tennis court, and you can see actually how much little the tennis court sees compared to the extremely large telescope, for example. So we actually will have a lot of improvement in terms of understanding the first galaxies, because those two last telescopes I showed, like actually those three last, right? The two optical telescopes and the radio telescopes, their main mission is to actually study this, right? Like James Webb. So we will see a lot of nice things in the next 10 years. So with that, I finished the presentation. I hope you have liked it, to know what we've discovered in the last 10 years, what can we discover in the next 10. And I hope we'll see you all in September when we come back.